Black body radiation spectrum, am I right? I have sent you one notes, okay? You have to go through that one and you come out with the questions, okay? This black body radiation spectrum, it is started by Kirchhoff actually in 1860. Look at here, Kirchhoff was very good, I think, experimental physicist. He did spectra of flame also, okay, and he did spectra of black body also, black body radiation spectrum, okay. So now later again black body intensity spectrum, it was unexplained actually. Later again in 1900 Max Planck explained it. Look at here, in this one we will get so much insight, okay, in this in the study of black body radiation spectrum we will get so much insight towards the subject actually, okay. So that's why, what is black body? First we shall start with this one, because we always have this question, okay. We say black body radiation, am I right? What do you mean by black body? Why they have taken black body, isn't it? What do you mean by black body? Quickly, anyone reply. Okay, that's a good idea. Okay, I'll make a Google calendar event on Google Meet so that you can join without permission. I think, yeah, you should say. Yes.
I think all
radiation are absorbed, isn't it? Whatever the radiation incident on it, it is completely absorbed. We call that one as black body, isn't it? Why they have taken black body radiation? Look at here. Any object which is when heated, it will radiate. Okay, we call that one as thermal radiation. Okay, thermal radiation. We are talking about this one. Okay, so thermal radiation. Any object, suppose if you take any metallic object, if you heat, it will become red. Then if you heat much more, it will become yellow, isn't it? It will go towards blue, isn't it? Its color will go towards blue, isn't it? That we have seen, isn't it? Now again, they could have taken any body. Why they have taken black body? Okay, so here comes the understanding. Look at here, black body absorbs all radiation incident on it. Okay, but our use of black body is not on absorption here. Okay, we are not dealing with absorption here, we are dealing with emission. Okay, black body is a very good thermal radiator. Is that okay? If you take any substance, okay, so okay, suppose if you take many substance, among them black body is a very good thermal radiator actually. When you heat that one, so compared to other body, black body will radiate more. Okay, it's a very good radiator, very good thermal radiator when you heat that one. So thermal radiation means, look at here, any body, if it is kept at temperature greater than 0 Kelvin, it will radiate. So maybe, so nearby 0 Kelvin, the radiation may not be so detectable. Is that okay? But it will emit the radiation. Is that okay? So again, now look at here. So black body is an ideal emitter. First one, okay? And second one is black body is a diffuse emitter. Yes. No, again, look at here. So again, if you take any object, when you heat that one, it contains electrons, isn't it? That electron will make oscillations actually. Atoms or electrons, it will make oscillation when you heat any solid. We are discussing solids here, okay? We are not discussing gaseous here, okay? Gas, when you heat that gas, suppose if it is atomic gas, it will give you discrete spectra. We are not talking about that gas, okay? We are talking about solids. Solids, when you heat that up, so again it will have some agitation, atoms will be agitated. Again, if you think of classical electromagnetic theory, if any charge which is accelerating, which is oscillating, it's going to emit the radiation. Is that okay? So that's why, whatever, again, we believe that at 0 degree Kelvin, everything is at rest like that. But we can't have 0 degree Kelvin, that's a different story. But at greater than 0 degree Kelvin, what will happen? That thermal agitation will be there. So charges will be oscillating inside any solid. So that will emit the radiation. Is that okay? Yeah. Now, why they have taken black body? They could have taken any body, isn't it? Because black body is an ideal emitter. It will emit more than any other body. when it is heated. Okay, it's an ideal thermal editor. Okay, I'm not saying that it will what you call emit radiation as it is. When you heat up, so compared to other body at some temperature, compared to other body, it's an ideal emitter. Is that okay? And it's a diffuse emitter. Suppose if you take a surface of a black body, okay, so again in all directions the radiation emitted is same. Actually the intensity of the radiation emitted is same. That will not happen with any other body. Actually it's a diffuse emitter. Can you grab the word diffuse? It's a diffuse emitter. That means it will not emit more in one direction, less in other direction. It will emit same intensity in all possible directions. Actually, okay. Later we pass that radiation through prism or spectrograph. Then we observe spectrum. Is that okay? Yes.
What is the natural frequency of the oscillator of this oscillation?
No, that will be, again, look at here. If you talk about natural frequency, there should be many natural frequencies, okay, in a solid. Are you getting my point? But later we will get into quantum theory here, okay. We don't talk about natural, yeah, so there will be natural frequency. So again, but energy of the oscillator is equal to nh nu, that kind of concept will come. Wait a second, okay. Yes. Now,
sir, we are discussing about matter wave radiation right now.
yes, solids when heated, it will radiate. Solid which is kept at temperature greater than 0 degree Kelvin, they will emit. We call it as thermal radiation. You have to see in Wikipedia. I think you will get much more idea. So thermal radiation. That thermal radiation, again, if you see how that radiation comes, again, it's because of oscillating charges only. Is that okay? Now look at here. That's why we take black body because of these two characteristics. I think I too had confusion. Why we take black body? We could have taken any body, isn't it? So because of these two characteristics. One thing. Yes.
It is also perfect observer.
Yes. That I have given. Am I right? So again, while doing the experiment, okay, we go again. We go for perfectly black body. So again, we can't, again, no surface is perfectly black body, remember. But we will construct that one. I hope I have given that diagram, isn't it? So we will take a cavity. We'll take a cavity with some opening. We'll take a cavity with some opening here. Okay. So then what we do here is we put a coil here, isn't it? Then we put some what you call a thermal insulator. Okay, suppose air is a good thermal insulator. You can just keep air over there. Is that okay? Good thermal insulator. So it has a very small opening. Okay, it has a very small opening, and inside we are going to coat black. What you call black color? Is that okay? So that and inside you can make it as a rough surface, so that light falls on this one. Should not reflect back into the same direction. Okay, you can just take care. I think I have given the construction. Okay, now this is some metal. I'll take this is some metal. Suppose copper. Okay, this is some metal, copper, rough surface like that. Okay, now look at here. This is the, again, you may define black body by, again, when whatever the radiation incident on this one, it will not come out at all, isn't it? It will be absorbed. It will have some multiple reflection inside. And so it will be absorbed so completely. Am I right? Suppose if you take any incident light here, it may go here. It will absorb, even though in the first incident part, even though it reflects little bit, it will be absorbed there only. Okay, after multiple reflection. But look at here. When this is heated, I'm going to put one heater here. Okay, when this is heated, it's going to glow. And it's going to emit radiation, and you have only one opening. Again, you can see radiation through that hole. This is a perfectly black body. This is a perfectly black body. When you heat that one, it's going to glow, and you can pass that one through prism or spectrograph, and you can find spectrum of that radiation. Is that okay? So this is the arrangement for what you call black body. So for observing black body radiation spectrum. Is that okay?
Sir,
Yes.
Because but I want to know why the black body radiation are emit all the radiation.
No. Again, look at here. All frequency. That's what you're saying. Am I right? Now look at here. This is a solid. Okay. This is not atom which is radiating. because of your transition by Bohr model. I think you are thinking about that one, isn't it? It is not because of that one. It is because of oscillation or something, oscillation of charges or something. Is that okay? So again, if you want to see the quantum mechanics of this one, it's so complex because it's a solid actually. Again, again, you can't determine energy level that easily and explain everything here. But again, our idea is different. Our idea is to study this black body radiation spectrum. You just hold on, okay? I can again. So this question you just ask that one again in Slack. Is that okay? No. Again, so again in the black body radiation spectrum, look at here. We don't again in case of absorption, we don't use this heater. Again, we need arrangement to have black body radiation spectrum. That means it should be a emitter, am I right? And we should have control over its temperature, isn't it? That's why we'll put heater, okay? In case of there is no role of this heater on any absorption, okay? But this heater will maintain some temperature. Is that okay? So that's the basic idea. Now again, you inside you have some metal. You take like that copper, iron, or something, okay? Now one very again, if you see the intensity spectrum. Or actually, so we are going to draw energy density per unit frequency. Okay, I'll tell you about this one. U of nu comma t as a function of frequency. Okay, it will look like this. For a particular temperature, it will look like this. Not symmetrical curve. Is that okay? Yes, again, suppose if you take T1, T2, T3, where T3 is greater than T2 greater than T1. I think I have given the diagrams, okay? So this is the, again, if you have radiation, again, you just pass that one through spectrograph, you can find the spectrum like this, continuous spectrum. As you said, again, there is no one spectral line. It's not because of atomic emission, okay? It's not because of atomic emission. It is because of thermal radiation, actually. Again, that's what we need to study here, okay? Now look at here. Now, the next part here is one more experimental. So this is the experimental observation, okay? Sometimes you can write intensity also here, okay? Intensity as a function of frequency also. You can write like that, okay? Now, one more thing that you need to observe in this situation, in this case, is this curve, okay? This curve, suppose if you have designed this one, this curve is independent of the material you quote here. Okay? It is independent of the volume. It depends only on temperature. Yeah. So now look at here, the next thing, the very notable point is it is independent of material and cavity volume, cavity geometry. This is very important experimental aspect here. Is that okay? Now again, this is what you call try again. So to explain this one again, many people tried that one. So before that one, we will have some more observation. Radiation emitted has continuous energy distribution. Wait a second, I'll get that file into. Now another one is for each frequency, energy density depends neither on chemical composition nor on shape of the object, but depends only on the temperature. Okay, it does depend only on the temperature. So temperature of the cavity wall, we say like that. Okay, frequency corresponds to maximum what you call intensity. Okay, this is frequency corresponds to maximum intensity, so that is proportional to temperature. Okay, so that means nu max proportional to temperature. So this is the maxima of this curve. Okay, so frequency corresponds to maximum energy density or maximum intensity, that is proportional to temperature. And one more thing what they have observed is total power radiated. Okay, total power radiated. Suppose if you what you call integrate this curve with respect to frequency, okay, total power radiated, so that's equal to, you just read out generally, A into sigma into T power 4. Remember, this is in watt per meter square. This is in watt per meter square. A is a dimensionless quantity. This A value between 0 to 1. This A equal to 1 for perfectly black body. A is less than 1 for nearly black body or any other what you call object here. Is that okay? Just quickly. Now this sigma, so this sigma, we call this one as, I think, Stefan Boltzmann constant. That's equal to 5.67 into 10 raised to minus 8 into 10 raised to minus 8 watt per meter square per Kelvin raised to minus 4. Watt per meter square per Kelvin raised to minus 4. Is that okay? So total power, if you integrate this one with respect to frequency, you will get total power per unit area. So that is proportional to temperature power 4. This is also another experimental observation. Okay, you better to call it as experimental observation. These things. Okay. So quickly, any question? Now, many people try to explain this one before 1900. One is by attempt by Wiens, other one is attempt by Relay. Okay. Look at here. This is also called as Wiens displacement law. So this can be written as, again, frequency inversely proportional to wavelength, isn't it? Lambda max into T is equal to constant. You can write like this. You can write this one as 1 by lambda or some constant by lambda or C by lambda actually, isn't it? So that you can take so lambda there, you can write lambda max into T equal to constant. We call it as Wiens displacement law also. Okay. So can you grab that file? No, send it via email. Yes.
Sir,
Yes, tell me.
sir, why the power depends on temperature on power 4? Power 4 by
No. Why we need to find, okay? Now look at, this is the experimental observation. So now look at here. Power is nothing but, power per unit area is nothing but area under the curve. The observation is that area under the curve is increasing as a temperature power 4. Okay. I think this graph might not be exactly correct. Okay. I think I need to increase this one quite rapidly. Is that okay? Yeah, exactly. We need to explain why that happened, how that happened, what is the what is the nature behind, again, what nature caused this whole thing. Is that okay? That's what we need to explain here, okay, in this experiment quickly. I hope you got my point.
Hello, sir.
Yes.
Hello, sir.
Yes.
If we draw a graph between energy density depends on lambda and T and lambda, what is the graph?
No. Then again, I think I have given that one. Okay, in the notes, that graph will be quite different from this one. Okay, I think I have given that one.
So mu is equal to C by lambda.
Yeah, nu equal to C by lambda. But again, I'll discuss that one. Okay, how to write this one in terms of other one. Okay, so nu u in terms of lambda comma T. Okay, many book will start with this one. They plot with respect to lambda. So then you have to write these things actually. Then you have to integrate with respect to all lambda. That's it. Okay, that's the only difference. Is that okay? So this is energy density per unit wavelength. This is energy density per unit frequency. That's what we say. Okay. So read out generally. I think you will get much more idea. But again, whatever you take. Okay. Whatever you take. Okay. I have given the curve of with respect to wavelength. Okay. Just check that out, because in Jatili he didn't draw that one. He has drawn with respect to frequency. Is that okay?
Sir,
Yes.
so suppose we change the degrees of freedom of the black body. What is the relation between?
How do you change the degrees of freedom? What do you mean by degrees of freedom of black body?
So one previous year question is, in the case of a two-dimensional black body, what is the energy density relation between temperature?
Two-dimensional black body. Wait a second. Two-dimensional black body.
At that time, the answer.
Wait. So what was the exact question?
I think it is the energy density relation of a two-dimensional black body with its.
No. That is related to this one. Okay. I think
Yes.
they might have given area. you have to, again, this is power per unit area, this one. They might have given some temperature or something, or some ratio or something. You should use this formula. Is that okay? So check that out. Two-dimensional black body means they might have given area of the black body. So that again, from that total area, so radiation will be emitted. Again, you are calculating power per unit area. Okay, so then you can multiply with area and you can do some steps here. Is that okay? Yes. Yeah. So quickly. So try to have understanding. Okay. Again, we shall solve problem later. Or again, if any unsolved problem is there, you put it into Slack so that I'll discuss in separate session. Okay. Because again, our understanding flow should happen here. Okay. In this one. Later we shall solve problem. Is that okay? Yes. Quickly. Now, next one is, what I'm thinking here is, again, with respect to wavelength, I have given in that notes, okay, just check that out. So attempt to explain all of this, okay, attempt to explain all of this.
Sir, what is two-dimensional black body?
No, two-dimensional, it's not about degree of freedom, okay, it's not about degree of freedom. Again, so there I made cavity to make it perfectly black body. Now they make some two-dimension like this, so that when you heat, that will be emitted, okay. Then they may relate some power per unit area. They may give the area of this one. They may give the temperature. Somehow it is Stephen-Boltzmann law problem, okay. So just try that out. Or yes.
The plate will be heat some temperature.
Yeah. So when this black body is heated, it will emit.
Yes.
Okay. So because that degree of freedom also comes in the theory, that's why I got confused. Are you getting my point? Degree of freedom.
Vibrating along two directions.
No, not like that. Not like that. If you take a planar black body, remember, if you see a microscopic thing, it will vibrate in all possible directions.
I mean, he is saying electrons.
No. Yeah, inside that one oscillator, if suppose they are vibrating in only two possible directions, something else would happen. Huh?
How can we say that the electrons will oscillate in some direction?
No. That's what they said. Am I right? Planar black body, isn't it? If you take it is mathematically infinitely thin plane, okay. But that's not the problem is, okay. Whenever problem is given, you should see the options first properly, and again, you should not overthink actually, okay. That's also the problem, okay. So you should not overthink. That means you may be thinking about its dimension is decreased, like not like that, okay. Again, black body radiation spectrum, it has nothing to do with the geometry of the black body. That's what I told. Am I right? So again, it is depending only on the temperature actually, and area obviously, total intensity. So that again, so total power. This is power per unit area. Am I right? Total power definitely depends on area, isn't it? So that's how you will multiply with area and you will do some stuff in that problem. Is that okay? Yes. Wait a second.
But the wavelength can be dependent on the size of the enclosure or size of the cavity?
No. Wavelength. No. How wavelength depends on size? No. Wavelength. Now look at here. You are receiving radiation. Okay. You are receiving. If you take tungsten bulb, you are receiving radiation. Okay. That contains many wavelength. Is that okay? That radiation, whatever we receive, that contains many wavelength. We pass that one through prism and we observe. We plot that curve actually.
Sir, what happens if I will release some monochromatic light?
No, monochromatic light. If you pass through prism, you will get only one. You will get only one spectrum.
But while proving Wien's displacement law, I have gone through that the wavelength is proportional to the size of that cavity. Or
No. Wien's displacement, lambda max may be proportional. No, lambda max proportional to T. Wait a second, we shall derive this out, okay? Then using equation you should try to explain, okay? If again, so you better wait for a while. Then I think most of the equation will answer your question, okay? You should be talking about lambda max, not arbitrary lambda, okay? Isn't it? Yeah, lambda max proportional to T. I'll come to that point. Yes. Now look at here. The next part here is Wien's. No, this is not Wien's displacement law. Okay, Wien's idea to explain this one. Okay, Wien's distribution. Wien's distribution. Wien's distribution law. You can say like that. Okay. Wien's distribution law. Look at here. I hope you have gone through statistical physics little bit. Okay. You have some idea regarding statistical physics. Usually probability of getting the system with some particular energy. This is e power minus beta into e, isn't it? E power minus beta into e. So again, using that one, using some statistical physics idea, see he derived this one. Okay, I too don't know. If you have any old paper or something, you just share into Slack. Okay, how Wiens exactly derived this one. Okay, so again, he derived this one using some statistical physics idea, nu comma t. So that is equal to some a into nu cube into, okay, some exponential factor e power minus beta. This beta is not kbt. Okay, here I have written e power minus beta e, that beta is equal to 1 by kbt. He has taken similar beta here. That's the quite confusing factor. Is that okay? Okay, but this beta is I better write b here, not beta. I'll write b here. Okay, so nu by t. Nu by t. Wait a second. Yeah, nu by t. Okay, I better not write beta. Where a and b are constant. Look at here. This fit the curve, most part of the curve. Okay, so okay, I think, yeah. Wait a second. I have some questions here. Why spectrum don't depend on atomic structure? Because it is not atomic emission. It is because of what you call agitation of atom that will happen in all solids actually. It doesn't depend on atomic composition. It is not transition in the atom. Okay, this radiation is not because of transition in the atom. Okay, that you need to. Yes. Now look at here. Just grab me. Okay, how exactly he did this one? I think. Yeah. Again, I need to check out. Okay, I read somewhere, but I couldn't get it. How exactly he did this one? A and B are constant. So okay. So now, how do you find A and B? Now look at here. This curve. If this is experimental data. Okay. Nu comma t. If suppose this is experimental data. Suppose if this is experimental data, look at here. Wiens curve versus frequency. Okay. Wiens curve was like this. Now again, you should one exercise is plot x cube into e power minus x. Plot this curve. Okay, you will understand this one. So exponential always dominates actually. Is that okay? So when x equal to 0, this is 0. Okay, in between you will have some maxima. Later when x tends to infinity, exponential dominates. So that again you will get 0 again. Is that okay? So this is experimental data, experimental curve. This is Wiens curve. In Jatili, he has given, he might have done some mistake on this one. Okay, in this one.
It comes from
Wiens curve, he might have done some mistakes. Okay. Yeah, obviously 0. I mean, so this functionality is x cube into e power minus x, nu cube into e power minus beta by t nu. Is that okay? So this whole functionality. So this one is Wiens curve because of this one. But actual experimental data is this one. It almost fits the curve, but at lower frequency regime, it is not fitting the curve. And you can find A and B using this what you call again. So this part of the curve is exactly fit. Am I right? You can take that part of the data and you can find A and B actually. So this part of the curve. So Wiens distribution fits the curve remarkably well at higher frequency regime. Is that okay? So relays distribution. So next idea. Okay, this is a kind of attempt. Okay, but now look at here. Again, I'm not discussing much because since this is not fitting that one, whatever the assumption he has done, I don't care about that one because that is not true. Okay, it might have fit one part of the curve, but that's not true. Is that okay? Yes. So relays law, relays distribution. Relays distribution. Relays distribution. Look at here. In case of relays distribution, again we discussed this one little what you call more because this is going to what you call this is going to lead to Planck's radiation law, which has a very what you call link there. Okay. TV1/3 constant. Wien's law. Wait a second, I'm not getting. Anyway, look at here. Now, in this case, look at here. You have radiation. Okay, you have a cavity. You have radiation inside that one, isn't it? You have a cavity. You have radiation inside that one when you heat that one, isn't it? Now, radiation consists of a standing wave, okay, whose nodes are at the cavity. That is the basic idea. Okay, suppose if you think there is a radiation, so it is forming a kind of standing wave whose nodes are at what you call, draw like this. Nodes are at the cavity. Is that okay? I am trying to draw it like this. Constructive interference kind of thing. Is that okay? I have drawn only one part, okay? So it will happen in all possible manner. Is that okay? So radiation consists of a standing wave having their nodes at a metallic surface of the cavity. So this is the first basic assumption that he has done. And again, one more thing he has taken, this is a quite drastic assumption, standing waves are equivalent to harmonic oscillators. These standing waves are equivalent to harmonic oscillator. Quite what you call strange concept, but actually if you have seen what you call field quantization and all that, I tried to explain actually field quantization. I think this assumption is not that bad. Okay, electromagnetic radiation, for energy of the electromagnetic radiation, we are going to apply harmonic oscillator concept, quantum harmonic oscillator concept actually. Okay, so that's why that's not that bad. But again, another idea, standing wave is equivalent to harmonic oscillator. Is that okay? That means each standing wave, each mode of standing wave, that's equal to 1D harmonic oscillator. Here we are going to assume like that. Is it okay? Now look at here. Now using this one, using the standing wave idea, suppose if you have, this is metal surface, this is metal surface, allowed modes should be like this actually. Again, allowed mode should be like this. Wait a second, how to draw? Allowed mode should be like this. Okay, so these kind of modes are not allowed. Suppose if it goes like this and after reflection, suppose if it comes back like this kind of modes are not allowed. Is that okay? These are allowed mode, and he's going to count number of modes in the cavity, number of standing wave, number of modes in the cavity, in the frequency range. Look at here, number of modes of standing wave per unit volume actually. Okay, we don't quote that one, per unit volume. So in the frequency range, nu to nu plus d nu. Okay, we can find this one. I'll try to share some more part here. Okay, so that again we are going to notify like this, n nu d nu here, that's equal to, look at here, 4 pi nu square by c cube into 2. I'll take this 2 outside because 2 is a 2 state of polarization actually. Is that okay? 2 state of polarization. Is that okay?
So how we found this?
No, that I need to check out. Okay, I think this comes in the laser theory and all, because cavity, we take laser cavity, isn't it? I have to think how exactly logically arrived at this expression. Okay, I'll give some links regarding how exactly you can do using wave theory. Remember, this is pure electromagnetic idea, electromagnetic wave theory idea. Is that okay? This is pure electromagnetic wave theory idea. Now look at here. So these radiations are in equilibrium with the cavity surface. These radiations are equilibrium with the cavity surface. Okay? No, this is 2 polarization state of light actually. Left circularly polarized and right circularly polarized. 2 polarization state, we say like that. Again, you are going to, you just find this one, you'll get this one. But for each standing wave, you will have 2 possibility. That's why the total number of possibility will be multiplied by 2. Is that okay? Total, again, if you just work out this frequency, wavelength and all, you will get this one. Okay, but total number of possibility is multiplied by 2, because there will be 2 possible, what you call, a normal mode with the same, what you call, frequency or wavelength. Is that okay? One is left circularly polarized, other one is right circularly polarized, like that. Okay. So anyway, we shall study these things. Okay, later in the later part of our subject. Okay. Now look at here. He is going to write energy density U of nu comma t, that is equal to n of nu into average energy. Look at here. He put average energy here. That average energy can be average energy of the standing wave, average energy of each standing wave, okay? Or that can be average energy of harmonic oscillator. Each standing wave is considered as 1D harmonic oscillator. Is that okay? Or that can be average energy of the oscillator inside the cavity. Anyone. Both should give the same answer. That is the idea. So this can be average energy of the, what you call, standing wave. Okay. Each mode. Okay. So as average energy of any one of the mode of the standing wave. Since the standing wave is equivalent to harmonic oscillator, you can just write that average energy of the 1D harmonic oscillator. Again, using statistical physics, 1D harmonic oscillator, how to write energy? Half mv square plus half kx square. There are 2 quadratic terms. If you remember equipartition theorem, suppose if you remember that one, that average will be half kbt plus half kbt. It will be kb into t. Or this may be the energy. Suppose you have cavity here. Okay, in cavity you have oscillators, isn't it? Are you getting my point? You have oscillator. That oscillator will emit the radiation in that direction. Okay, I have taken only one direction here. If you take one direction, what will happen? This oscillator should be oscillating like this actually. Is that okay? This oscillator should be oscillating like this. So then look at here. So again, this may be either average energy of the standing wave, that means average energy of the harmonic oscillator, or it may be average energy of the oscillating charges on the cavity also. You can say like this. On the cavity, there are charges which are oscillating, isn't it? So there are atoms or electrons which are oscillating. Okay, this may be the average energy of that one also. You can put any one, but you will get the same answer, kb into t. Yes, speak out. That's why here I thought of that dimension. We say 1D harmonic oscillator. Okay, this average energy is average energy because of 1D harmonic oscillator. Look at here. Lot of assumptions will come here. It will make us lot more uncomfortability, remember. But these assumptions are not true. I'm going to explain that one. Okay, these are to fit that curve, isn't it? They were trying to fit that curve. So coming out with some assumption. Is that okay? So now this part was almost correct. This is equal to 8 pi nu square by c cube. After taking this factor 2, this is nothing but kb into t. But if you plot this one, remember, if this is experimental plot, this will give like this. This is parabola, am I right? This again u proportional to nu square. It's a parabola, isn't it? It's a parabola. It will fit the curve only at lower frequency. And one more thing is integral of u of nu comma t 0 to infinity d nu. It is tending to infinity. What is this one? This is the total energy. Am I right? If this is energy density, this is the total energy, isn't it? So total energy density. So now that is tending to infinity. That means cavity contains infinite energy. We call this one as ultraviolet catastrophe. It cannot happen, isn't it? It cannot happen. Okay. But one thing is, again, he found this factor. Okay, this factor. Okay, he found that factor 85 nu square by c cube, which is the same factor will be there in Planck distribution also. Okay. And one more thing is, in this part he has taken classical harmonic oscillator. In this part he put average energy of classical harmonic oscillator, which is in thermal equilibrium at T. Okay, we are going to study this one in statistical physics, how this happens to be KBT. Okay, or if you need that idea, I can give you like that. So e power minus beta e, this is the average energy, am I right? So according to your canonical distribution, so E into e power minus beta e dE, energy will run from 0 to infinity, energy of the oscillator. I'm talking about cavity oscillator. I'll not take average energy of the radiation. Okay, that doesn't look good. Okay, but his idea was like that. He's saying standing wave is equivalent to harmonic oscillator. Then he put, because this is energy density of radiation, isn't it? Whatever we have seen outside, that is energy density of radiation, isn't it? That's why this should be something related to radiation. That's why he said standing wave is equivalent to harmonic oscillator, and he put harmonic oscillator, what you call average energy. Is that okay? So let me tell you how to find that average energy. Okay. Now look at here. So one more part here is, again, you can, again, in place of this one, you can put average energy of the oscillating charge inside the cavity also. Both are equivalent. Is that okay? So again, inside the cavity, you will have oscillating charge. Those oscillating charges or oscillating atoms, whatever you take, those will be in thermal equilibrium at temperature T, where beta is equal to 1 by kBT here. So then statistically, so in statistical mechanics, we are going to find it like this. This will give you Kb into T. Beta is equal to 1 by kBT. This will give you Kb into T. So try to work out, again, we shall work out this integral later, okay, infinite integral, gamma function, okay. Or you can use equipartition theorem also. Suppose if you write E is equal to half m Vx square plus half Kx square. Each of those oscillator on the cavity, so one dimensional oscillator model, so two quadratic term, you can take half kBT plus half kBT. We call it as equipartition theorem. If you don't know any of this, don't worry, we are going to study all of this whole black body radiation. It will again come in the what you call statistical physics. Okay, you don't have to worry. Yes, tell me. Yeah, so tell me quickly. Somebody called me.
Is this the statistical approach?
Statistical mechanics approach only. Again, this one. How do you find that average? Look at here. We are using probability distribution here. This is a probability distribution. This is probability distribution actually. Probability of finding the system at energy E that is proportional to e power minus beta E.
So whenever the distribution comes, we are saying the statistical one. The probability.
No. Distribution means, look at here. He was talking about curve. He is talking about curve, I think. Statistical distribution is different. You are talking about Fermi-Dirac distribution. Yes. Those are occupation probability. So that will come little later. Okay. Again, in the approach of what you call Bose, it is so that kind of distribution he will derive actually. Here we don't derive that statistical distribution, but this is that probability distribution. That is similar to that one. This is similar to that one. E power minus beta E. Yes. Are you getting my point? Statistical mechanics approach. That's what I'm saying. Okay, this part, or you can use equipartition theorem, because the idea is the oscillating atoms or oscillating charges are in thermal equilibrium at temperature T. Then statistically we can write like this. Okay. Yes. Any question? Quickly. So continue. If you have any question, quickly ask. No. Whenever I stop in the middle, you ask the question. Is that okay? Are you getting my point? I stop and I'll wait for your question, isn't it? You quickly ask the question. That's the best idea. Is that okay? So that again, I'll be waiting for your question, isn't it? Then you stop and ask that one. Okay?
The integration is from 0 to infinity.
Yeah, look at here. Oscillator, am I right? Some oscillator may have what you call zero energy. Some oscillator may have very high energy, isn't it? So possible energies of the oscillator, that is from 0 to infinity. Classical energy of the oscillator, springs, oscillating spring, it can be at zero energy also. It can have infinite energy also, isn't it? Are you getting my point? So that is the basic idea. And energy is continuous. Energy of the oscillator is continuous. That is the idea here. So that's why it didn't fit well, isn't it? That's why it didn't fit well. Is that okay? Energy of the oscillator in the cavity is continuous. So because of our statistical physics, it gave us Kb into T, and it couldn't explain higher frequency regime. So quickly, any doubt? Quickly. Now look at here, Planck's distribution. No, I mean, you may have a lot of doubts here, but it will be, most of the doubt will be cleared after statistical physics. Okay. Now look at here, Planck's distribution. Okay, CK. Planck's distribution. Is that okay? Now look at here. All of these things contain some basic idea, isn't it? Look at here. Planck didn't edit this part. Number of normal mode per unit frequency, kept that part as it is. Is that okay? Planck didn't edit this part. So what Planck did was, he edited this part. He said radiation is at thermal equilibrium with a cavity. Okay, radiation is in thermal equilibrium with a cavity. So that's why average energy of the radiation should be equal to average energy of the cavity oscillator. That's the very better idea, isn't it? Average energy of the radiation, again in place of average, this should be average energy of radiation, because this is the parameter corresponds to radiation, am I right? We are seeing this is output radiation energy density, isn't it? This should be parameter corresponds to radiation, isn't it? Now look at here. So this should be average energy of the radiation, but that average energy of the radiation is equal to average energy of the oscillator, because radiation and oscillators are in equilibrium. They are exchanging energy. Radiation and oscillator are in equilibrium. They are exchanging energy. He did two very drastic. Oh, look at here. So this is equal to average energy of radiation mode, actually, okay, one mode, okay, radiation mode, that's equal to average energy of oscillator on cavity wall, because this radiation is in equilibrium with the cavity wall. It is exchanging energy, and he did two very important assumptions. Radiation exchange happens in a discrete manner. Sorry, energy exchange between radiation and matter happens in a discrete manner. Now look at here, we are improving our understanding. These all experiment, this explanation, it is improving our understanding. We knew about radiation, we knew about matter, isn't it? Now radiation and matter, what you call, exchange energy in a discrete manner. Improvement in our understanding, isn't it? Now radiation matter exchange energy in discrete manner. That means, look at here. If you have radiation of frequency nu, okay, if it gives energy to the, what you call, matter, it should give in the form of NH nu. That is the idea.
In the oscillators.
Yeah.
Those oscillators.
Suppose radiation gives energy to oscillator, it should give in the form of NH nu. If suppose oscillator gives energy to radiation, it should give in the form of NH nu. Where nu is the frequency of oscillator, actually. Nu is the frequency of oscillator now here. Is that okay? Now look at here. One more assumption is oscillator energy. Cavity oscillator, okay? Oscillator energy sometimes that standing wave itself called as oscillator. Okay, I think in case of laser physics and all, cavity again, that standing wave itself called as oscillator. Sometimes, yeah. So that's why he says that standing wave is equivalent to harmonic oscillator, isn't it?
The modes of the number of modes n. That can be also said that n is new.
Yeah, again, yeah. No. What I'm saying is that is also named as oscillator. As you remember, the standing wave is also called as oscillator. But here I'm talking about cavity oscillator, oscillator on the surface of the cavity. Are you getting my point? Yes. Oscillator energy is quantized, is itself. If oscillator energy is quantized, definitely energy exchange will happen in a quantized manner. Okay, oscillator energy is equal to E is equal to N H nu, where nu is the frequency of the oscillator. Yes.
Why the radiation is taken to the harmonic oscillation?
No, that is a kind of assumption. Okay, he says again, each standing wave is equivalent to one-dimensional harmonic oscillator. I think I'll try to explain in harmonic oscillator model, quantum harmonic oscillator model. Okay, I'll try to touch that one to field quantization. Then I think you may get some idea, because those models are same actually, but I don't know how they got that intuition. Okay, how they said that one, I don't know that one. What is the main basic behind saying that oscillator is equivalent to 1D harmonic oscillator? But this assumption is okay. In this assumption, what we say, again, this should be average energy of radiation, but radiation and cavities are in equilibrium. Radiation and oscillators are in equilibrium. That's why average energy of the oscillation is equal to average energy of the radiation.
So audio is not coming.
Anyway, we shall quickly continue here. Oscillator energy is itself is quantized. This is the another assumption that is made by Planck. Is that okay? But actual, in our later we shall see, it should be n plus half h bar omega, like that, n plus half h nu, not again here n will be equal to 0, 1, 2 and so on. Okay. Now if oscillator energy is n h nu, okay, now average energy according to statistical physics, there should be summation. So into n h nu e power minus beta n h nu, is that okay, where n is equal to 0 to infinity, summation over e power minus beta n h nu. So just read out Jatili very carefully. He has given what are those summations. Okay, what are those summations when you put n is equal to 0 to infinity? That integration is replaced by summation, and here you get very important factor, that is h nu divided by, try to work it out. Okay, he has given in the footnote, he has given the summation, and have a note on that one, because that summation may be needed in statistical physics. Okay, have a note on that part of mathematics. I think one is this might be geometric progression if you put n equal to 1, 2, 3 and so on, denominator part. Numerator is, I think, arithmetico-geometric, isn't it? N equal to 1, 2, 3, but so this also power like that. Okay, so that kind of thing, just try to work the mathematics. Okay, so he has given in the footnote, that's equal to h nu divided by e power beta h nu minus 1, where beta is equal to 1 by kBt. Okay, here beta is equal to 1 by kBt. That b is different. Okay, in Wien's law, that b is different. This beta is equal to 1 by kb into t. And now when you substitute, so u of nu comma t, that's equal to 8 pi nu square by c cube into, what is this one, h nu divided by e power beta h nu minus 1. This fits the curve 100%. This fits the curve 100%. And from that curve, you will find this h actually. Look at here. This is the first, y force is equal to 1 into ma, y f is equal to, f is proportional to mass into acceleration. Force is proportional to rate of change of momentum. Alright, why can't you write proportionality constant 2 over there? No. F equal to 1 m into a. Why can't you write 2 m into a? Quickly, anybody answer? Why you write in case of Newton's second law, F is equal to 1 ma. Why you can't write 2 ma? Well, again, force is proportional to rate of change of momentum. You define like that, am I right? Why can't you write proportionality constant 2?
Because we have defined unit force.
Yeah, that is close, but yeah, still better understanding. Yes, quickly. Now look at here. That is the first time force is defined. And you had freedom to define 1 Newton of the force. That's equal to when 1 kg mass moving with 1 meter per square acceleration. That's the first time you defined Newton. Force, the concept first time came. That's why whenever first time this concept came, you put a proportionality constant of your interest actually, isn't it? I mean, here energy and nu, isn't it? These are different values, isn't it? Different dimension. And you need this one. This is a proportionality constant, Planck constant. We say that as Planck constant. NH nu. Is that okay? Are you getting my point? So this is the first time quantum idea came for the first time here. Are you getting my point? Quantum idea came for the first time. This H plays a kind of proportionality constant. That's what I'm saying. Is that okay? But it is natural, okay? That's a different one. That question is different one, okay? Whatever I have asked. You had a choice of defining one force over there. You had a choice of making proportionality constant 1, but this is a universal constant decided by the nature. Are you getting my point? You can't make it 1 here. So there should be some factor here, isn't it? Now that factor is found from the curve itself. Now this will fit entire curve actually, okay? This will fit entire curve, no doubt, okay? So if this is experimental data, so so this one also give exactly same shape, no doubt. But what you do is, in a reverse way, you take experimental data, you fit that one, you find Planck constant. How Planck constant is found first time, isn't it? Using experimental data. Because it fits very well, remarkably well. Just like I found A and B. A and B is found, again in case of Wien's distribution, A and B is found from the experimental data, from high frequency regime, where Wien's distribution used to fit well, isn't it? So similarly, so this used to fit entire curve, okay? This used to fit entire curve. Using this one, experimental data, they'll find H, okay? They'll find H. This is the first time he defined that one, quantization. That's why since that concept come first time, proportionality constant came. Are you getting my point? New constant came, isn't it? Earlier we had no universal constant, do you remember? Earlier I have written E is equal to half mv square plus half kx square in case of classical harmonic oscillator. No, this is universal constant. This is decided by nature actually. This is decided by nature. That role is there, isn't it? No, E proportional to frequency. I'll tell you how this might have happened. Look at here. You remember nu max proportional to temperature. This was again from the plot. Okay. So now if you put Kb into Kb here, this is of the order of energy. Energy. This should be energy. It means somehow energy is decided by frequency. I think from there they might have got that idea. Energy of the radiation depends only on frequency, not on amplitude or something. I think this might have gave that idea. So that is the photon concept is also like that, isn't it? Like I hope you try to explain that photoelectric effect using wave theory, isn't it? Energy of the radiation, from this side, if you come from this side, or I'll write it like this, T proportional to nu max. So put Kb here, isn't it? Kbt is an energy factor, am I right? So again, look at here, energy of the radiation. Energy of the radiation is decided by temperature, no doubt. Kbt is the thermal energy, isn't it? That means energy of the radiation is decided by frequency. Isn't that? I think they might have got from that idea. Energy proportional to frequency of the oscillator. Energy of the oscillator proportional to frequency. Is that okay? But it should have, because this is joule, this is per second, am I right? Hertz. You should have some constant here. You can't make this one 1. That is decided by nature. Are you getting my point? That is, again, why I said, because, again, that universal constant comes in the new, this is the first time we are introducing new things, isn't it? Suppose Boltzmann law, isn't it? That's the first time he introduced that distribution, isn't it? That's why Boltzmann constant came, Kb, isn't it? Gravitational constant. That's the first time Newton introduced that law. So this is generalized one. This is the beginning of Newton's second law, is the beginning part, am I right? But later you define force, isn't it? You put one law, isn't it? So this is the framework, isn't it? This is the most general one. Newton's second law is the most general one. That's the beginning part. That's why you put proportionality constant 1. Since you put proportionality constant 1, in the gravitational law, you put different proportionality constant. Because once it is decided. Now, once energy is defined well, frequency is defined well, isn't it? Now you are relating them. Force is defined well. You have mass m1, m2 by r square, isn't it? While connecting them, you need proportionality constant, which decide, whose order decides everything, isn't it? 10 to the power minus 11 in case of gravitation, isn't it? Universal constant, which comes in that kind of new concept. Universal constant comes, and one more very disturbing fact is that universal constant is changing actually, little bit, okay? Not that measurable thing. Have you heard? Anyone heard of this one?
No, sir.
These universal constants are changing little bit, and we don't have theory for that one yet. We don't have even we can't even imagine that one. Okay. Now look at here. U of nu comma t as a function of nu. Now this is also again E equal to n h nu. It's a kind of quantum idea, isn't it? Similar to your Bohr-Sommerfeld quantization. Is it? It's a kind of quantum idea. I mean, it came before Bohr and Sommerfeld. Okay. Yes. Now do all of further step. Okay. That means example 1.1, integrating this one throughout frequency and showing that this is proportional to t power 4. Okay, this is the total area under the curve. That is nothing but power. That's the one part. Again, write in terms of what you call wavelength. Differentiate with respect to lambda. Equate that one to 0. Find lambda max into t equal to constant. Or you can differentiate this one with respect to nu. You can show nu max is proportional to temperature. Is that okay? So that means you have to locate this one. Am I right? Nu max. How do you locate? You have this whole function. You just differentiate and equate 0. Again, once you equate 0, you will get this point actually. You'll get this value. Again, that value is proportional to temperature. Is that okay? That are the other exercise. Example number 1.1 means displacement law. And outside the chapter, he gave one more example. I'll give that one in the assignment. Okay. No, that change in this universal constant, that's very new concept. Okay, it is very low change. Okay, I think we can't measure in our ordinary lab. I don't think we can measure that one. Yes.
When I got to know that the oscillator, one-dimensional oscillator, so that oscillator becomes like harmonic quantum harmonic oscillator.
No, that is the idea. He says oscillator energy is quantized. Oscillator of frequency nu, whose energy is equal to n h nu.
But the oscillator has some ground set energy n plus r.
This is not pure. This is not a framework. He assumed.
Yes.
This is not a framework of the theory. That's why quantum theory is developed, remember. Are you getting my point? Now look at here. This is not a framework. That's why that half h nu is not there here, where n starts from 0 actually. It says quantum harmonic oscillator can be at 0 energy, isn't it? Yes. That will not happen in our actual sense. Yes. But this is not the framework. But some assumptions are still true, whatever he did, because this is explaining the curve, am I right? Then backside assumptions are true. What is that assumption? Energy exchange happens in a discrete manner. That is still true. If you take photon, if you take quantum harmonic oscillator, that is still true. Are you getting my point? That's why again it will improve our understanding. Okay. So now with that assumption you proved this one. Okay. Harmonic oscillator energy should be quantized. Might be there may be quite error as you said, but it is quantized. That concept is true. And energy exchange between radiation and matter, that happens in a discrete manner. That's also true. We should accept the basic assumption now. Yes? No, but in his assumption, it's not pure. It's not pure. E is equal to NH is wrong, but energy of the oscillator is quantized. That is true. Are you getting my point? It may have a mistake, but that basic assumptions are true, isn't it? Because using that basic assumption, you got this one. Using that one, what you call it will fit the curve remarkably well. That's why that assumption should be true. So that's how Schrodinger equation, you should believe Schrodinger equation. Whatever may be the assumptions in designing that one, but once you solve that one, once you find the application which explain all of the experimental aspect, then you should believe that one. Are you getting my point? So very, very similar here. But our understanding improved. What is that understanding? We had radiation. I'm saying in reality it is not zero, but in Planck's idea, he took it can be zero. Are you getting my point? This is not complete theory. That's what I'm saying. This is not complete theory. But some assumptions are true, isn't it? If you are not taking this one, if you just say think that energy of the oscillators are quantized, they are not continuous. That's still true in quantum harmonic oscillator. That's what I'm saying. Yes, quickly. Are you getting my point now? Quickly. We are improving our understanding here, okay? Don't ask again whether it can be zero. Yeah, it is not zero. We know that one because I studied quantum mechanics already, isn't it? This is not my beginning, isn't it? This is a historical beginning. Are you getting my point? But in that idea, yeah, that's a mistake. Even in the Bohr-Sommerfeld quantization also, it will give the same answer.
No mistake, it's an evolution.
Yeah, it's an evolution. That's correct. It's not a mistake. It's an evolution because if you think at their age, you can't even imagine that one, isn't it? How much difficult to. They had no internet. They had no information sharing. Remember, they worked a lot. Yeah. So one more thing here is I think Bohr-Sommerfeld quantization will also give the same answer. He has given in the later part. Just check that out. Or whether it gives n plus half h bar omega. I don't remember. Bohr-Sommerfeld quantization. Anyone? No. Just forget about this universal constant which is changing. Okay, I too don't know much about that one. Just for curiosity, to make you curious, I told about that one. Okay. Yeah. This is not exactly true, but some part of these assumptions are still. Look at here. He has taken radiation as electromagnetic wave, isn't it? That is not true, isn't it? That is not true. Bohr? Same result, isn't it? Same result in Bohr-Sommerfeld theory, which we call old quantization, which used to explain some experimental fact, but that is not a framework of the theory. That is not a framework. That is not exactly correct. That's what I'm saying. According to that one, oscillator energy can be zero, but quantum mechanics will not allow that one. Okay? Yes. I hope you got that point. I think somebody asked about that one. Whether can be zero. No, it cannot be zero quantum mechanically. We shall see that one later. Okay? Now, one thing that you need to observe. I hope you will do later part of the mathematics. Okay? That is integrating this one. You might not have the knowledge of one integration. Take that integration as it is from the book. Some Riemann-Zeta integral, I think. Okay? And differentiating, equating to zero, finding Wien's displacement law. I hope you can do those two parts. Okay? Or I'll do it in the next discussion session. Okay? Yeah, quickly. So now we shall try to improve our understanding. How did you find this one? This is exactly Rayleigh's idea. Number of normal modes using standing wave and all, isn't it? This is EM wave theory, am I right? How did you find this one? This is classical idea. Classical physics means electromagnetic theory, classical mechanics. Together we call that one as classical physics. Okay. Now what is this one? This is new idea. This is because of new idea, quantum idea, isn't it? So this is because of quantum. So quantum idea, because we can never think of oscillator whose energy is quantized, not continuous. Am I right? Classically, its energy is half mv square plus half kx square, which is continuous. We can't even imagine this one classically, isn't it? But this part is derived by quantum idea. This part is derived using classical idea, isn't it?
So then how do I integrate energy density?
How do you integrate? No, again, integration with respect to d nu, that's it. Again, you have nu here. It will be proportional to d power 4. Integral 0 to infinity u of nu comma t d nu. If you integrate, that new functionality will go. This is proportional to t power 4. That's nothing but power proportional to t power 4.
But there is the discrete one, summation one, h nu, the e to the power beta h nu.
No, look at here. We are talking about one oscillator. There are many oscillators with different nu on the cavity. We are talking about one frequency here. Are you getting my point? One natural frequency. Somebody talked about natural frequency, isn't it? I think this nu is this E equal to NH nu. Am I right? You write like this. Where nu is, I think, called as natural frequency of that harmonic oscillator. Are you getting my point? Yes. Now, one part is because of what you call classical idea, other part is because of quantum idea. How both things can be clubbed to make one equation? It's a kind of fit, isn't it? So that's why this whole assumption is not exactly correct, isn't it? So again, what Bose faced was, Bose was a teacher, I think in either in Calcutta or in what is that? I don't remember. Another Dhaka University. Yes, yes. He was a teacher over there. He was a professor over there. While teaching, he used to face this one. Now look at it. You ask some questions here, isn't it? I faced some trouble, and I try to develop that one, isn't it? He faced lot of trouble in explaining this one. Is that okay? And in explaining this one to student, this is not correct. Is that how one can be from classical, other can be from quantum, and you club and you make one equation and explain that one. That's why this derivation is not completely correct. Are you getting my point? So then what he does is, in 1923 or 24, I think, okay? I think by yes, tell me, any question?
So here no immediate temperature transfer. How can say that energy depend upon the temperature?
Wait.
So here no temperature term. How can say this equation is depend upon the temperature?
No. Beta is equal to 1 by kBT. That I didn't read. Right. Beta is equal to 1 by kBT, okay? I think in statistical physics, it will come very frequently. That's why I've written directly, okay? Yeah, it is depending on temperature. So quickly ask, okay? I mean, clarify all of this. 1905, photon concept came, isn't it? And when that Compton effect? 1923, isn't it? Compton effect. Now we know that, again, by 1923, it is very well known that so light composed of photon of energy is equal to h nu, momentum is equal to h nu by c. Now inside the cavity, whatever you have, electromagnetic radiation, that should be thought, so that should be treated as it's a collection of photon. It's a gas of photon. Is that okay? The gas of photon. That is the idea proposed by Bose for the first time. You should treat that radiation inside the cavity as a gas of photons. Is that okay? Of different frequency, obviously. Is that okay? Of different, because whenever you see emitted light, you got range of frequencies. Am I right? You got a spectrum, continuous spectrum. Okay. But energy of each photon is equal to h nu, where nu is the frequency of the radiation. That's how we define. Momentum is equal to h nu by c. By 1923, I think it was very clear I think by the time I think Bose gave this idea, I think in 1923 only he gave that idea, I think. 1924 or 1923 to 1924, okay? I think it was very clear that light composed of photon. But Planck had no idea like that. Are you getting my point? He just extended Reilly's idea. Are you getting my point? So now, so what he does is, again, he derives this whole thing. Again by treating electromagnetic radiation as a gas of photon and independent of wave theory. Look at here. I'll try to explain that one, okay? This will come again in statistical physics. Don't worry. If you are not understanding anything, don't worry, okay? I'll try to explain that one. It is like this, okay? In that case, we go for phase space concept, okay? We go for phase space concept. In phase space, what we do is, we do dx, dy, dz, and we do dpx, dpy, dpz, okay? So we integrate over all the region actually. Or we write this one as d cube of r, d cube of p actually. Is that okay? Wait. This is the volume of the phase space. We are going to divide that phase space into phase cell of each of volume h cube, Planck constant. So this is number of phase cells. Okay, in the phase space concept. Okay, I'll explain all of this in statistical physics. Don't worry. Okay. So now, so this is number of phase cells. Okay. Let me try to derive that one. You may not understand completely. So now this will give. Look at here. So once you do this one, once you do this d cube of r integration, you are doing integration throughout the cavity. You will get volume outside. Okay, you will get v by h cube into integral of d cube of p. We write only one integral, but there are 1, 2, 3, 4, 5, 6 integrals actually. Then what we do is to find number of possible states or something, whatever we have found, n of nu, isn't it? What we do here is, we are going to we go for phase space. We are going to integrate this d cube of p in a spherical shell region of inner radius p, outer radius p plus dp. We are going to integrate this d cube of p in this region because we need number of state in the range nu to d nu. Okay. Wait, one second. Hold on, one second. Now, nu to d nu, isn't it? Now look at here. P is equal to h by lambda. P is proportional to nu. Can I write like this? In case of photon also, you can write P equal to h by lambda. Photon momentum proportional to nu, that I have written h nu by c, isn't it? So that means if you need number of state for nu to d nu, that corresponds to number of state for p to p plus dp. I'll give brief idea, okay? Not complete idea. Is that okay? Yeah. So any problem?
No, sir.
Yeah. So that's why. So to find that one of number of state between nu to d nu, we go for integration of this one by p to d plus. So again, integration in this region, p to, total number of state in the range of momentum of the photon, which varies from p to p plus dp. Then what will happen is this will be v by h cube 4 5 p square dp. It will happen like this. I hope you got some part of that one. 4 5 p square dp. Now quickly. Again, I'll take per unit volume. Is that okay? Then volume will go. Anyway, let me keep volume. V by h cube 4 5. What is p square? H nu by c whole square. What is dp? D h nu by c. V by h cube 4 5 h square nu square by c square. H by c I'll take outside, isn't it? D nu. H cube got cancelled. What is this one? V 4 5 nu square by c cube d nu. But I'll take per unit volume. This is nothing but my n of nu. Not over. Bose did that one by taking phase space concept, dividing phase space into phase cell of volume h cube, okay, and counting number of possible states of the photon. Okay. Now, each photon state can have two possibilities, left circularly polarized or right circularly polarized. He has taken that factor 2. Look at here, for electromagnetic wave, you can think of polarization. How can you think of polarization for photon? Are you getting my point? These are very intuitive idea. For photon, how do you think of polarization? So can you keep your audio off, someone? Yes. For photon, how do you think of polarization? Are you getting my point? So that's the first idea. Actually, that photon polarization is very closely related to spin concept actually. That in 1923, look at here, quantum mechanics started from 1925 by Heisenberg, 1926 Schrodinger, like that. Remember, spin concept came very later. So spin concept was not there. But he said that it's left circularly polarized or right circularly polarized, or we don't have exact Bohr's work, how he got this factor actually. We have only Einstein's work. Let me tell you the history, or you can just read out that textbook. Is that okay? What I have given, that book, okay? That's not textbook. So that's, yeah.
It fits with spin concept.
Yeah, it is related to spin, but he didn't call it as spin because spin concept was not there. I think he might have called this one as two state of polarization of photon only. Are you getting my point? At that time. Because of law, they had not much, what you call,
So what
understand.
in the board, the lower portion, lower left corner, what is lambda nu?
Lambda, where? Lower.
Lower left portion.
No, n of nu. N of nu. Number of state, d nu. Sorry, n of nu, d nu. N of nu, that's equal to 8 pi nu square by c cube. Am I right? Okay, first part of that one portion of Planck law. Okay, it is derived like this. It's not over. Look at here. It's not over. First part you derived, isn't it? Other part, in case of Planck law, you derived by assuming what you call cavity condition. Now, other part should also be derived using photon by taking gas of photon. Am I right? This is something related to gas of photons, isn't it? Gas of particle, isn't it? Other part should also be what you call explained using that one. So then what he did was this n nu is over. Okay, this part is over. Now other part here is what he did was, again, that we will derive in statistical phase. Okay, photon statistics. We call that one as photon statistics. Okay, so again, while deriving that one, we take total number of photon is not conserved. It can vary. Total number of photon in a cavity is not conserved at all. Are you getting my point? So that means photon will be absorbed and emitted by the cavity. Okay, at one instant of time, you can't say that total number of photon is conserved. That's the first idea that he has taken. Photon number is not conserved. Okay, one. Other one is distinguishability. Now you again look at here, you got total number of state. Okay, now you have to multiply with this one with occupation probability. Okay, occupation probability. I'm going to call it as f of h nu. Occupation probability. So each of the state, again, what is the probability of occupation like that? Okay, photon, each photon state, what is the occupation probability like that? Okay, and then I have to multiply by h nu. Then I will get energy density. Are you getting my point? To find this part, he assumed photons as indistinguishable. Remember that indistinguishability came after quantum mechanics. That idea of indistinguishability came after quantum mechanics. Are you getting my point? But he assumed before quantum mechanics indistinguishability. He assumed total number of photon is not conserved. Using all of those ideas, he gave this one 1 by e power beta h nu. We shall derive this one. In Reef, he has given 2 to 3 different way of deriving this one, photon statics. He derived this one. Is that okay? And multiply with h nu. Yes, this is distribution function actually. This is a photon statistics, photon distribution, you can say like that. Or Planck distribution also. Sometimes we say Planck distribution also. Very old one, isn't it? Actually, we write energy E here, okay? Remember. So this 8 pi nu square by c cube. I better write this one. 4 pi nu square by c cube into 2, that's equal to u, isn't it? Spin concept, phase space concept. Why would you divide phase space? Why he would divide phase space of the volume h cube? Why he might have divided phase space of volume h cube? Don't say at that time uncertainty principle was not there. Are you getting a point? How many intuition exist in this whole thing? Or maybe once he started this idea, he might have got this should be done like that. But basic intuition is very important, isn't it? Are you getting a point? At that time, quantum mechanics was not born. At that time, there was no concept of uncertainty. Look at here. Uncertainty is taken care. Spin concept is taken care. For a particle it's difficult to define even think of. We say now polarization state of photon and all. We say we are going to use that one in quantum communication. Actually, that's a recent one. But at that time, you think over it. And here, indistinguishability. So spin, uncertainty principle. Okay. In this one, indistinguishability. Now, photon number non-conservation. Photon number non-conservation. These ideas are introduced by Bose, and he gave alternative derivation to Planck distribution. Not only Planck, black body radiation spectrum distribution, if I have to say like that, because Planck didn't edit this part actually. Is that okay? Quickly, now you ask the question, quickly.
Sir, how that division of H cube is related to uncertainty principle?
Now look at here. So in phase space, again, if in phase space, suppose I'll take only one dimension, okay, px and x, okay. If suppose px and x are very accurately defined, then that will violate uncertainty principle. Then what we say is we are going to divide phase space into phase cells. We are going to say particle is anywhere in that cell by respecting uncertainty. I'll explain this one in statistical physics. Are you getting a point? If you say particle state is defined by a point in phase space, that will violate uncertainty principle. A point in phase space corresponds to one well-defined momentum and well-defined position. That is not acceptable according to uncertainty principle, isn't it? This is what you call, so 2-dimensional phase space, but here you have to go for 6-dimensional phase space because 3 dimension actually, 6-dimensional phase space actually. I'll explain that one. Yes. Now look at here. Bose tried to publish this paper and that was rejected. Is that okay? Then he has written a letter to Einstein, which is saying, respected sir, I have ventured to send you the accompanying article of your perusal and opinion. Look at here. Actually, he published and it is rejected because that he was Indian, definitely. Because it was, I think, obviously post-independent era, 1923, isn't it? So pre-independent era. No. So that's why I think, because look at here, he gave, at that time, you had photon concept, isn't it? This was the alternative derivation which should be acceptable by any paper, isn't it? But he sent that one to Einstein, and by writing a letter, look at here. In the letter, what he says is, I derived what you call this 8 phi nu square by c cube independent of the classical electrodynamics, and I could be able to give alternative derivation. And he says, so please arrange publication in some German publication. I can't pronounce that one, okay? And he says, so in the beginning, he says, I am the one who's translated your paper to English. Okay, actually, General Theory of Relativity is written by Einstein in German. Bose translated that one to English. Okay, so but in the letter, what he writes is, I don't know enough German to I don't know enough German to translate my paper to German. Maybe that may be true. Okay, I mean that translation from English to German may be quite difficult. German to English may be quite easy, isn't it? In one side may be quite easy. But I think that was a kind of, he was lying. He was trying to seek the attention, because if your paper is rejected, what you do? You have to go to big scientists, isn't it? If they accept, then definitely it will be published, isn't it? It's very well known. So then Einstein didn't look into that one. I mean, he didn't take that one seriously. After some time, he found that, yeah, this idea is correct. After some time, he found that this idea is correct, and he published that one again with S.N. Bose. And later, Einstein got the idea that, yeah, we can consider as a gas. We can do some statistics. Look at here, quantum statistical mechanics. This is a birth of quantum statistical mechanics before quantum mechanics, and he has taken that idea. What is the idea? You can treat them as a gas of photon. And you can do this all indistinguishability, everything you can do, isn't it? And he published other paper on condensation without mentioning Bose. So when I planned to start this coaching class, I thought I would give the name of Einstein or what you call Dirac or Schrodinger, like that. Then at that time I was reading this textbook, okay? And not only this, later I attended many seminars also, okay? Then I found that I think, yeah, we should be proud of this person. So again, it is no. I was thinking about Schrodinger, Einstein, or something. Einstein Physics Learning Center, Schrodinger Physics Learning Center. Then I got that, yeah, we have a person whose thoughts were equivalent to Einstein, or maybe better. Who knows? Yeah. No, Einstein was also legend, isn't it? His each of ideas lead to different stream actually. I'll tell you later. But equivalent to Einstein, isn't it? If there is one person who can be matched with Einstein, that is S.N. Bose. So, but later Bose tried to collaborate with Einstein, but Einstein didn't allow him. Later, I think he worked with Marie Curie on some crystallography or something. So yeah, so that is the history. Okay, I'll share some video or some conference video if possible on that one. Yeah. Now, any question quickly on the concept here? We are going to derive this one in a quite different manner. Okay, in case of statistical physics, I'll go for some
Sir, I am not giving the
uncertainty.
How can you say this?
No, because of uncertainty only you gone for phase space. You divided phase space into phase cell. Why would you divide phase space, isn't it? Are you getting point?
What is in your
Phase space is three-dimensional.
No. This phase space is it has, look at here, 1, 2, 3, 1, 2, total 6 dimension. For 3 dimension particle in 3 dimension, phase space will be 6 dimension. I'll explain this one. Okay, don't worry about this part. If you have any question regarding understanding, now look at here. Yes. Yes, speak out.
What is in your
N new. Which where I have written?
Number of particles and
Okay. This is number of state actually. Possible number of photon states actually. Total possible number of photon state in the frequency range nu to d nu. Possible number of photon states. Photon can be in this state, in this momentum state, in other momentum state. Photon can be in this phase cell, in other phase cell. Each phase cell corresponds to state of the particle. I'll explain this one. Okay, I'll explain this one later. It will be very convenient because lot of things clubbed here actually. Statistical physics idea, some other idea, these things clubbed here. I think you will understand at the end of the course. Okay. Why 1 by h cube is introduced? That's what I asked. Am I right? Now we say it is because of uncertainty, but I don't know how he got that intuition, because whatever the paper published, that is published by Einstein. We don't have original Bose work at all. We don't have any paper or any work or any even derivations, whatever did by Bose. And he was a person, he was too shy. And I think Yeah, what to do? If you had that work, I think maybe. What is the?
Maybe each cube is used for dimensional consistency.
Yeah, maybe that is total number, isn't it?
Why each is the dimension of momentum?
Huh. H is the dimension of momentum. That's true. Yeah, maybe. But no, we don't know what Bose thought. Okay, we don't know that one. We can say maybe, as you said, that's one of the valid answer. You get my point. This is the angular momentum cube. This should be angular momentum cube. Like that. That's correct idea. And we do the same thing in statistical physics. We don't write H. We write some H naught. Then we, while respecting uncertainty, we write H naught should be equal to H.
Sir, the cumulative part gives total volume of that cavity.
Then I have taken this total volume. I have taken because this is per volume. Okay, that's why I have
And if you are considering cells, each cells, so having delta X, delta P with the uncertainty part, we are dividing by that part, delta X, delta P, delta Y, delta P.
No. What is this one? This whole thing is phase space volume. Okay, this whole thing is phase space volume corresponds to the momentum of the photon P to P plus dP. Okay, this whole thing is phase space volume corresponding to momentum of the photon P to P plus dP. For small range of momentum of the photon, there will be some phase space corresponds to that one, abstract space. Okay. Now, if you divide by H cube, you will get you are dividing that phase space into volume, and you are counting how many number of cells are there of the volume H cube here. That is the role of this H cube.
Yes, sir.
How many number of phase cells are there? This is a count actually, but we say per unit volume later. This is energy density per unit volume. That's why I haven't taken this volume of the cavity. This is volume of the cavity. I told like that, isn't it? This is the volume of the cavity. Okay.
Sir, what is capital NV?
No, that is number of state of the photon, possible state.
Sir, the nu is the number of oscillations.
Earlier he said nu is number of modes, isn't it? No, not number of oscillators. Now look at here.
Density of the state.
Wait. State is defined by, suppose if you take quantum state, ground state, first exit state. I think you might have heard of that one. Hydrogen atom, ground state, first exit state, like that. Those are states, am I right? So similarly, if there is a free particle, photon is a free particle, am I right? Its state should be decided by position and momentum, but they are not accurately defined. That's why we divide that one of the phase cell. You will understand this one accurately, okay? I did lot of interpretation on phase space. You don't have to worry. So that's why that state we are counting. What is the possible number of states of photon? With the frequency, photon may have different momentum, different direction, isn't it? With frequency range nu to d nu, it can have different direction, everything, isn't it? That's what we have integrated. I'll give the exact idea. Later again, try to watch this video lecture again, okay, after statistical physics. Is that okay? There we do it quickly actually using density of state concept. I use density of state concept to derive this one, not even phase-based concept, okay? But both are related actually, okay? But that's what I'm saying. Are you getting my point? Speak out.
Sir, the H cube term is there, no, sir. It is similar to kind of like we were deriving in tensors in special coordinates. Is it?
No. Here tensor concept won't come. No. Tensor concept comes in the transformation. Wait a second. Here we are not talking about transformation from one to other like that. One thing. Is that okay? And other one is this H cube term comes because to balance the dimension that is the one possibility. Other one is, I'll tell you in statistical physics, to make a number of state countable. Otherwise, again, if all points in phase space are the possible state, how many points are there on a plane? Infinite. That's uncountable. That uncertainty makes it countable actually. This is the one count, am I right? You got to count. If each and every point in the phase space is a possible state, just like classically, isn't it? Each and every point is a possible state because there is no uncertainty classically. Then number of states would be uncountable. To make it countable, we divide by h cube. I think that is Boltzmann idea. Yeah, I think that is Boltzmann idea. Is that okay? That was very earlier. I think Boltzmann law was very earlier than this one, Bose idea. I think he has taken that one from Boltzmann idea, but look at here. He has taken Planck constant. That's also very important part here, isn't it? Is that okay? Yes. Yeah. Shall you close here? Do the later part, and if you found any difficulty, yes. I'll explain this one, okay? 4-5 p square dp, how this happens, okay? In statistics. N new part? Speak out. Can you hear me?
Sir, I cannot understand the next state.
Possible state means, look at here. If there is photon which is moving in this direction with momentum h nu by c, that is one momentum, am I right? P1, can I write like this? If that is a one possible state actually. I'll explain this one, okay? I'll explain this one because in the beginning of statistics, I spent a lot of time on this one. You don't have to. So suppose if the same magnitude, but if it is moving in this direction, we say there is another state of motion. Momentum direction also decides state of motion. Are you getting? We are collecting all of those possible states. Is that okay? All of those possible state of motion actually of the photon. That is n into nu. Is that okay? This is now this idea doesn't require any classical theory. Is that okay? Yes, quickly. Actually, classically, yes. Yes, I'll explain that one. Okay, in statistical physics, I'll explain why position and momentum decide the state. Everything I'll explain. Okay, position and momentum is a state of the particle actually, classical state of the particle. Okay, yes.
Generally, how to find the Planck constant values, sir?
Now you got this one. Am I right? Now this curve, this function is exactly same as that function. Then you take that data, you try to fit that one, and you find this one. You take many points in that one, okay, and you can find that Planck constant. One idea. Other idea is photoelectric effect. That is the easiest way to find Planck constant. But initially Planck constant is found. Again, you got this one. You have some constants in this one. We call it as empirical. You can call it as empirical constant. Later it is found that it's a universal constant. Okay, E equal to h nu after Einstein's idea. Later it is found that it's a universal constant. So again, it is treated as empirical constant by fitting this one to what you call curve. You have experimental data for some particular temperature, isn't it? So for different frequency, you have data. Am I right? From that data, you can find this one. Is that okay? Initially, it is found by, again, experimental data, fitting that one to experimental data. Later, again, in lab, again, now we have better method, that's photoelectric effect. If we have a good setup of photoelectric effect, we can find Planck constant. Is that okay? Yes. Any question? N nu may be number, yes. N nu is number of photons. Okay, I'll explain all of this. Okay, but try to grab some ideas here. Okay, that's it. Now our understanding is now forget about Bose idea. Okay, forget about Bose idea because now we are just after the Planck idea. Whatever we have, energy exchange happens in a discrete manner. Energy of the oscillator is quantized, but we had no generalized theory. We need to move on to building the generalized theory, isn't it? That is the next approach. Okay.